Good morning, myself Kavya. This presentation introduces my research titled AI Driven Automated Cyber Risk Assessment Pipeline for GRC Intelligence, a tripartite framework. The work mainly focuses on building an AI system that converts three key cybersecurity domains, such as CVE vulnerabilities, mid-tier attack techniques, and NIST controls. The main goal of this project is to move from technical vulnerabilities to a governance, risk, and compliance intelligence that is fast, automated, and operationally useful for both security and GRC teams. In this digital era, thousands of vulnerabilities are recorded in the National Vulnerability Database per year. So, organizations are facing an overwhelming volume of threats and vulnerabilities. But even though in this digital era, most of the risk assessment practices remain highly manual and fragmented, which take more and more hours. So this will affect both the cybersecurity and GRC team to struggle due to delays and inconsistencies. They struggle not only to determine which vulnerabilities are most critical, but also they struggle to understand how they may map to concrete attack techniques and NIST controls to avoid the exploitation. So existing studies are highly rely on expert judgment and static documentation, which are slow, error prone, and difficult to scale in a continuous vulnerability disclosure environment like National Vulnerability Database. So in the meantime, the vulnerability can be exploited, the chances of vulnerabilities can be increased. The central research question of this work is to what extent does an AI-driven tripartite framework automate, improve cyber risk assessment, and support GRC decision making? So this question captures three dimensions: automation by reducing the manual effort, improvement by enhancing predictive mapping and performance, as well as the GRC support, producing outputs that are directly useful for GRC activities rather than remaining on a purely technical level concept. So this research has three core objectives. The first one is to build a hybrid machine learning model by integrating both structured and the text descriptions with the use of sentence embedding for the severity predictions. The second one is to create a rule-free semantic pipeline that maps both the vulnerability that maps each vulnerabilities to the techniques that can be used to attack the vulnerabilities, as well as the controls that should be implemented by an organization to avoid the attack. So this is the mapping was done with the cosine similarity scores. The third one is to implement an interactive assistant that accepts both CVE identifiers and the free text vulnerability descriptions, that returns severity, attack paths, and control recommendations. Thereby, it produces a reusable knowledge layer across all the three frameworks. Based on the literature survey, the previous work has addressed only some parts of this problem. Some studies map vulnerabilities to controls or techniques, but typically in pairwise method. Some studies use rule-based matching and manual exploitations or supervised models that do not scale well, as well as some studies do only surveys on this. Without connecting the output to attack behavior or complaint requirements, there is a lack of integrated tripartite solution that simultaneously perform severity classification, semantic mapping, and GRC orientation explanation over large dataset. Methodology follows the CRISP DM framework, which is well suited for the industry aligned projects. Starting with the business understanding, the work frames the operational GRC pain points identified in the literature survey. The next phase is all about the data understanding preparation in all three dataset, including exploratory data analysis and handling class imbalance perfectly. The modeling phase develops from baseline to hybrid approach, followed by the evaluation using metrics chosen for GRC relevance. Then the system developed a tripartite knowledge graph visualization and a final deployment operationalized through an interactive assistant. Modeling approach is is stacked and comparative. It begins with the structured only model using only the CVSS metrics in XGBoost and LightGBM as a baseline. Then it introduces text only models using TF-IDF representations. Finally, the modeling approach moved to the hybrid models of combining both the features, both the structure and the text features using semantic embeddings. This assessment shows like how much additional value does the semantic information brings to the severity predictions rather than the structured studies. Next is the model evaluation. It demonstrates a clear performance gains as more expressive representations are introduced. The structured only models achieve moderate accuracy but struggle with minority classes because of the severe class imbalance of the CVE dataset. Next, the text only models improve the accuracy and macro F1, showing the importance of the descriptive text informations. The third one is a hybrid model, which combines both the structured and the text informations, and it used sentence embedding and achieve an accuracy around 81 to 83%, as well as the macro F1 score around approximately 0.72 to 0.74. Beyond the classification, this framework computes three mappings using sentence-BERT embeddings and the cosine similarities to avoid the black box magic. So each CVE is embedded in the same semantic space as Metayer attack techniques and NIST controls, which enables top-K similarity-based retrieval. The system also generates three mapping files: CVE to Metayer, Metayer to NIST, and direct CVE to NIST controls. So this rule-free embedding-based approach works using learned semantic representations, so it can easily process huge collections of cybersecurity text automatically. The visual output is a tripartite knowledge graph creating using NetworkX, which integrates the top K mappings across all the three frameworks, and it makes the visual easily interpretable. So the nodes are colored and the edges are weighted. The edges are done by weights. Next, the output of the interactive assistant looks like this. It accepts either a CVE identifier or a free text vulnerability description. Then it goes and predicts the severity and provides class probability distribution, and then returns top 3 Metayer attack techniques and top 3 NIST controls, as well as for each Metayer attack, it gives the possible NIST controls as well. This work makes three primary contribution by providing hybrid severity classifier, then a semantic embedding relationship using tripartite mapping. This builds the knowledge between all three frameworks, and the third one delivers a production-ready assistant prototype that transforms raw vulnerability information into a GRC-oriented intelligence. So, closing the gap between technical findings and governance requirements, this framework also opens some future extensions, such as it can be extended by integrating different frameworks like ISO 27001 and CIS frameworks, and it needs ground truth validation, as well as the system can be developed using advanced language models like GPT. This is the conclusion. This concludes the presentation of my framework. Now I'll demonstrate the artifact in action. First, the demonstration jumps into Jupyter Notebook. Here, the basic exploratory data analysis was done. It shows there are some missing values as well as severe class imbalance in CVE dataset. And it also proves day by day, yearly there are so many vulnerabilities published. Jumping into the modeling approach, it begins with the XGBoost model on the structured only data. Due to class imbalance, the model is not performing well. So it highlights the importance of balancing the classes across the large data set. So after doing manual soften weights and feature engineering, the XGBoost model shows a significant improvement both in accuracy and macro F1, but it lacks in the lower, the minority case like low, and it acts too much on the highly severe class like critical. Then I trained an LightGBM model, which also shows identical results as XGBoost. So jumping on the models doesn't make any sense. Then I moved to a curiosity-based analysis, which is text-only analysis. So I used the TF-IDF representations and trained logistic regression, which shows a good performance compared to the structured-only model. Then I also trained an XGBoost model with the same representation, which shows a significant improvement both in accuracy and in macro F1. It also handled the minority class as well. Due to computational power and time, I moved to Google Colab Pro. Basic data cleaning was done, and I started with hybrid model, which uses the CVSS metrics as well as text description. So the model performed very well on the combined features, as well as I trained the above model was trained using TF-IDF representation, and here I trained a LightGBM model with the same TF-IDF representation, the hybrid approach. It shows a small improvements on both accuracy as well as on the F1 score. Then I jumped into the multi-layer perceptron, which uses the sentence BERT embedding on the text information. So this also gave an identical results as XGBoost and LightGBM, but the LightGBM performed better than the XGBoost. Early stopping was done. Classes were handled properly. Then I jumped into the Metair attack and the NIST controls and created embedding files for all the 3 datasets using sentence embedding. After doing the mapping like CVE to Metair, Metair to NIST, as well as CVE to NIST, the assistant can learn from all these informations. And I also did a graph-based analysis, a tripheriate knowledge graph for a visual interpretation. So here is the interactive assistant. If I run this, it asks me, so if I query this assistant with a CV ID, from the dataset, it provides the description of the CVE ID, the probabilities of all the classes, as well as the severity of the vulnerability IDs. It gives top 3 Metair attack techniques and top 3 NIST controls to prevent that. And it also gives top 3 NIST controls for each Metair attack. Then it also serves a visual graph representation of the above work. So what this assistant is doing is it internally retrieves the CVE description and the structured CVSS metrics. It applies the pre-processing pipeline and then passes both structured features and the sentence bed embeddings into the hybrid model. And here is the free text vulnerability. If I give a free text vulnerability into this assistant, it will also do the same thing as you did for the CVE ID from the dataset. So this is not from the dataset. This is a free text vulnerability description. Whatever the user gives to this assistant, it does the same mapping for this free text as well. So thank you so much. As we see, this would typically require manual reading of NVD entries, entire pages, and disk control catalogs can now be achieved in a few seconds with a reproducible, explainable pipeline. Thank you.